10.2. Magnetic fields and force on a moving charge. Around a magnet is a magnetic field, which you call a B field. At every point in space, there is a magnetic force, and we can see that force using a compass. The unit of a magnetic field is called the Tesla, after Nikola Tesla, capital T. Magnetic fields can be visualized with field lines. And here are 3 examples. Notice they go from the North Pole to the South Pole. And the more lines in one area means a stronger field, just like it did in electricity. So here, notice it going from the north to the south. On this middle picture, these are iron filings, and they actually show the magnetic field lines. They automatically line up that way. Since currents, which are moving charges, make magnetic fields, then other magnetic fields apply a force to a moving charge. For a moving charge to experience a force, the charge must be moving. The velocity vector of the charge must have a component perpendicular to the magnetic field. And the formula, the little arrows above are indicating their vectors. So the force vector equals the charge times the velocity vector, cross product with the magnetic field vector. Now, most of you haven't taken pre-calculus, so we haven't done cross products. So in short, we can do it this way. QVB sine theta, where F is the force, Q is the charge, V is the speed of the charge, B is the magnetic field, and theta is the angle between the speed and the magnetic field. The direction of force on a positive moving charge is found using what's known as the right-hand rule. It's the right-hand rule, meaning you have to use your right hand. The fingers always point in the direction of the magnetic field. The thumb points in the direction of the moving charge, and then your palm faces the direction of force on a positive charge. So you can see on the picture right here. So the fingers are going the direction of the magnetic field. The thumb's going the direction of the moving charge. And the palm is the force on a positive charge. Now, to make things easy, we have to have 3 dimensions. So if it's into or out of the paper, it means into is pointing directly into the sheet of paper, out of the paper is coming up out of the paper. I'm going to say up is towards the top of the paper, down is towards the bottom of the paper. The force will be 0 if the velocity and the magnetic field are parallel, because sine of 0 is 0. So a moving charge would be unaffected. So we have to have some component of the velocity of the moving charge be perpendicular to the magnetic field. In this picture here, the reason why the charge goes up is because your fingers would be pointing that way. So those are your fingers. Your thumb is going to be pointing the direction that it's moving. So your thumb is going that way. And so then your palm is pointing the direction of the force. That way. It's a terrible picture. So it's your fingers, your thumb, and then the force is that way. The motion of a moving charged particle in a uniform magnetic field, uniform meaning it's all the same, would be circular. Here's why. So if I take position 1 at the bottom, so you can see here, this is the right-hand rule for it. The X's mean it's going into the paper. So X means into, a dot means out of. The dot means out of. That's because we use arrows for vectors. If the arrow is going away from you into the paper, you see the feathers, hence the X. If the arrow is coming at you, you see the tip. It's a dot when it's coming up out of the paper at you. So, and back to our diagram over here, the magnetic field is going into the paper, so our fingers point into the paper. And the particle is moving towards the right, so the thumb is going towards the right. And then the palm is facing up, so the force on a positive charge is going up towards the top of the paper. So that means it's being forced up, so it's going to curve up. When we get to position 2, your thumb would be going there, your fingers are going into the paper still, and now your force is that way, towards the left. So it's going to curve around there. Once we're up here, our thumb is going left, our fingers are still going into the paper, and our force is coming down towards the bottom of the paper. So curve it over to here, and at this point, our thumb would be going down, our fingers are still going into the paper, and our force is going towards the right. Bend it around that way. Formula was force was QVB sine of theta, but it's going in a circle. Centripetal force was mv squared over r. So I make those equal to each other because the magnetic force is causing the centripetal force. And I solve for r. The sine theta disappeared because theta is 90 degrees. Sine of 90 degrees is 1. So I have QVB, will be R times the QVB, and then divided by that. So it'll be MV squared over QVB. The V, one of the V's cancels, so our radius of our circle is mv, the mass of the particle, times its speed, divided by the charge and the magnetic field. You can use that to study the particles. So this is a bubble chamber, so we had some charged particles here. They come from nuclear decay. And by knowing the direction of the magnetic field, we can tell what kind of particle they are. So, because particle 1 went that way, and we knew the magnetic field, we knew it was negative. That one, particle 2 is positive because it curled the other direction. Particle 3 was bending the same direction as particle 1, but it has a much larger radius. So either it's going faster or it's lighter or something like that. You can also use this to determine what type of atoms there are. So we can use a mass spectrometer. Down here in the ion source, we've taken unknown material and we've broken it down to individual atoms, and they're shot out at a known velocity. And they enter a known magnetic field, and we've given them a known charge as they come out. So we know the charge, we know the magnetic field, we know the speed, and so then if we measure the radius of their curve, because we have detectors over here, we can figure out their mass. From their mass, we can decide what type of atom they are.